for this first part, as Ariel said, the point is to introduce you to techniques to profile Python code and consequently to optimize your code so it can run faster than it would if you don't go through that phase. For this part, I'm going to use a type problem. Of course, I would expect that what you do in your research is slightly more complicated. But the point is to showcase some techniques. Okay. So the type problem I chose is the quicksort algorithm. If you are familiar with computer science, you mostly know what this is. If you are not, it's basically an algorithm to sort an array of comparable elements, so numbers, for example. So the problem is given a collection of orderable elements, so I can compare them together. How to sort them efficiently with regard to computational time. So I want sort them and I want sort them fast. And there exists many different sorting algorithms. I will use only one of them, which is considered as the fastest and most general purpose one, and the quicksort. So here is let's see. Here is a nice visual. It's from Wikipedia. A nice visual GIF, whatever you want. And on the side, the algorithm actually to perform that. There is basically two main steps, which is the partition, the second step, and the positioning of the pivots. Okay, so starting at the beginning, so you pick an element, you choose an element from the collection, and that element is called the pivot. Then you have to know where you should place your pivot, and you do that by partitioning the array of numbers. So you put all of those that are smaller or equal on the left, all of those that are greater, strictly greater to the right, and you put the pivot in the middle. So the idea is the steps are pretty simple. I won't explain why it is efficient. I won't go into a complexity theory here. But that's the main steps, and you repeat that until your array is sorted. And you repeat that on each subparts of the array. So each part that is not sorted, because once you put everything on the left and on the right, those smaller and greater, you know that the pivot won't change. It's on the right place. Okay. If you have struggled to understand that, I mean, that's understanding deeply the algorithm is not really the point. The point is to show you code that's is so at the beginning, and to move forward and to show you how to improve it. Okay, so don't panic. So first implementation, as often you start with some code. Here I have the two steps I mentioned. So the swap. So I basically change two elements in an array. So here it's Python. I do that on one line. You can do that on several lines, but the idea is just I change the position of two. It's very simple. And here is an implementation. If you are familiar with that algorithm, you may you may not agree with what I've written here. That's exactly the point, actually. So I do it in the following way. So I have two values, I and j. I initialize at low +1, and I move j so that it reaches the end, and I move I so that it ends up being the position of the pivot. So I know that between 0 and I have all the smallest ones, or all the smaller ones, or equal to the pivot, and all those from I to j, ultimately being the end of the part I'm working on, being the elements that are strictly greater than my pivot. And I do it in a certain way that is not very efficient, but we will see how it's not efficient. So this is my first implementation, and well, this is the algorithm. So binding together the two first pieces of code, and this is a recursive function, by the way. So it's a function that calls itself. It's basically just a nicer way to write to loop. Okay, so don't be afraid of that. So I initialize low and I, which are the bounds. So that's how I partition my array. I choose a pivot. Here I just choose the first element of the array. There are different ways of choosing it, but I mean that's not. I won't go complicated here. I just choose one, and then I partition it. I swap the pivot well, I put the pivot where I should put it once I know its position, and then I just recurse. So just call again the same function that does the sorting part, but on a part that here is between the low bound and the pivot position, and then between the pivot position, just one, and I, so on the two subparts of 0, okay? So now I want to test my function. I want to make some benchmark datasets so that I can have an idea on how efficient or inefficient it is. To do that, some guidelines that I will mention a bit greater details later, but here, what I do is I have one function that produces an array, and it doesn't really matter actually about the numbers. All I need is that they are comparable. So I just use random integers, and I just had some fun here extending. This is just me building a list of numbers, shuffling it so it's random, and that's it. And I store them into one variable that is arrays. By the way, all of that is a notebook. So if you're on the Indigo website, you can download either the PDF version of it or the notebook. So it's actually some real code that you can run yourself if you want, if you have a Jupyter installed. So I have several different samples of arrays of the same amount of numbers. Here I have 20,000, so it should be sufficiently large in order to have some metrics to measure. So here is a checklist of what, in my opinion, makes a good benchmark. Depending on your use case, of course, it can change a little bit, but the idea is to have enough different samples so you can generalize on what you're doing. That being said, if you know in advance the characteristics of the data you will work on during your research, by all means, make something that looks enough like your actual data, or if you can use actual data, use actual data. It's always there. But you should take care to not take too much to speed up development. If you need to wait hours to have metrics, this will slow down a lot every optimization process you can make. So if you have to wait at most a few minutes, it's best. Especially in the early stages where here my code is it works, but it's a bit broken. So I don't want to wait minutes where I could wait just a few seconds, obviously. Depending on problem, you may not have the choice. Some problem actually work with a lot of data. Think about biology, typically, well, you cannot have a small genome. It doesn't work that way. And very important, you need to have the same data across the different ranks. That's why I have stored my arrays into one variable, and I will copy those arrays all the time. The reason is that if you want to compare the performances of different versions of your code, the data must be the same, because if you have an increase in speed and the data is not the same, you don't know if the increase is because of your work or because of the data being different. So you need to have the same data in order to have results that are comparable. Okay. So to test that, I have a driver program. So this is what basically I will use to measure my metrics. Okay, so it's I make several runs. So here I make 10 times I make the same work. So for every array in my list of arrays, there are 50 arrays. I copy the array so that I don't alter the original data. And I run the code. Here's my quicksort algorithm. And then that is very important too. I test the result, because if you suddenly have an enormous gain in speed, but it's because your code doesn't do what you want it to do, well, that's not the way you want it to work. You want to have your code that actually does the work you want it to do. So you need to test your code. That is absolutely, well, that's one of the most important thing, the most important thing you have to ensure. So here it's pretty easy. In sorting algorithm, I just check that every element, the next one is either equal or above it. And okay, checklist for driver program, like the benchmark. Ensure repeatability of the runs. So that's echoes, keep the same data, copy them, don't alter them. Well, again, do not alter the benchmark data. Don't break your code. Test it. I mean, I'm saying that sometimes I don't have my own code, so I don't know. I mean, we all do that kind of mistakes. But when you optimize things, it's really important to keep that in mind, because if you spend days optimizing something and after, I don't know, 3 days of work, you realize that it doesn't do what you want it to do, you basically lost 3 days of work. So it's that is not good. make several runs to reduce the impact of the noise. So what about the noise? The noise is, you need to keep in mind that what you run on the machine, that machine can run other processes that you have no control on. So the performance of your code may depend on the environment in which it runs. For example, if you work on Windows and suddenly Windows decided to download an update for some reason because it's Windows, you will see an impact on performances, but you have no control of that. You cannot know that just looking at those numbers because the program you run has no idea on what is going on the side. Okay. So yeah, for reasons out of control, the system may soon run slower. So yeah, you can reduce that with this. Reduce all the possible interferences. So if you have a browser open, close it. If you have other programs running, just shut them down to ensure that the code you benchmark should be about the only code that runs on your computer. So now that we have a driver code, the benchmark, and the code to analyze, we can perform some analysis. So here I want to introduce you to two tools. The first one is cProfile. The second one is Line Profiler. They are similar in what they do, but they are used for different things. You see. So profiling, if you don't know what it is, this is a definition from Wikipedia. So in software engineering, that is a process, an analysis of either the space, the memory. I will not show you, I know Ariel said otherwise, but I will not show you memory profiling because of time constraints, but I will show you a CPU profiling. Time complexity of a program, so this is more theoretical. Usage of particular instructions, and that is also important, but most of all for us today is the frequency and duration of function calls. So we want to know which functions are called and how often they are called and how long they take. Okay, and the analysis itself is useless if it leads to nothing. Here the point is to actually aid program optimization. So going hand in hand with profiling is the optimization process. Okay. So cProfile. So here this is a Python script also. So I just import cProfile and I use it that way. This is context manager. Well, if you are familiar with Python, you know what this is. And I just create here a profiler and I run the main function in there. So very simple lines of code. Something I advise you to do, especially if you work on a cluster, is to not perform any analysis at this stage. What you should do is to dump the results or the metrics of your analysis on some file that you can examine later. Because if you have everything on the same script and you realize that the output actually is not what you're looking for, you need to run the whole profiling step again to have some results. You lose time. So write it on a file, especially if it's on the cluster, so you can copy the file locally on your computer and perform some analysis there. You don't need performances to analyze a text file. You do to run everything. You can do that from the terminal. So with that line of code, typically, of course, you replace those things by your code. This is the output file, and this is your script. And now that we have that file, we can examine the stats. Okay. Yeah, here I want to have something visually nice, and I couldn't do it without using Panda. You probably don't need to use Panda. So don't really look at that code. It's there for the sake of completeness, but don't look at it. The important line is this one. This is how I load a file that has been written by some optimization process before. And well, this is what I do. So I sort using the cumulative time in the descending order, and I can show you this. So I have my main function that takes some time. The cumulative time is, of course, the total time. You see the number of calls. Main is called only once. It's makes sense. The quick sort is a recursive function, so it's calling itself again and again. So it's called a lot more than of course the main function. The partition is called the same amount of time because I have one partition per quick sort, so it makes sense too. The swap function is called a lot, because it's called inside of the partition. It's called inside of the quicksort algorithm. So does this called a lot. So that one we need to have a look on what is going on inside. And the rest is a Python built-in function. So here you can see all this is used for the assert clause. This is used to get the length of the list. I have no real control on that. So what is of interest are the four first lines for me. So I can, those are bash lines of code, but so don't mind the exclamation mark before. It is in order to run bash in notebook. I can do that on the terminal. That translates my file, here the file I produced, into some other file that is a dot, okay, the dot file that represents the call graph. So the description of the call graph, and I can translate that into an image. And I like it very much because this gives me this, which is a lot more visual than the lines I showed you before. And we can see a lot of interesting things here. The colors go from red to deep blue, going through going through green. So if you see something in bright green, it does not mean it's good. It means it's actually well, in between red and blue. We don't see that here, but there is an example later. So you have the percentage of the time taken by each function in there. The first percentage is that, and the second percentage is the time actually spent on that function and not inside of another function that is called by that one. So main takes 100% of the time, but the time spent on main is negligible. Quicksort itself actually takes only 10% of the time, which is okay. So it's not that much. Then partition and the swap are seem to be the two functions we need to focus on, most probably partition. So that's what we can see with C profile. So that's nice. That's very nice. But there might be an issue is that we don't have an idea of what takes some time inside of those functions. We just know what functions actually take some time. So small review of C profile before moving forward. So it's nice because it's built in Python, so you don't need to install anything. If you have a running Python interpreter, you have C profile. It's non-intrusive, as you can remember. The code is very simple. It's just that. I mean, that's literally 4 lines of code if you count the last one. It's really easy to set up. It's very verbose. You didn't say that because I use a pandas to filter other things, but it's very verbose. So you want to examine that file locally and don't just try to read it from the terminal. So you need sorting, filtering. There will be an exercise later. But as I said, there is no in-depth analysis of the code. So that's what we might be interested in. So now we need to open the black boxes. The concept of black box is basically the colored box we had previously. We don't know what's inside. We want to know what's inside now. And to do that, we are going to use a line profiler. So this is another tool that is it's pretty nice. So I tried to make it as non-invasive, non-intrusive as possible. So this is the way I do it. So I import line profiler, and I create a line profiler that way. And then I add functions. So I want to examine partition, quicksort. I didn't put the swap function because it's only one line of code, so it doesn't make a lot of sense to have to add it explicitly. But I want those two. And then I need to wrap the main function here inside of the profiler. So I have a new main function that I can call to examine the metrics, the profile actually of my code. And as before, I advise you to dump the stats on some file that you can examine later for well, because it's more convenient. And here, this is how in another script later, the next day, whatever, you load the file into yeah, some profiling stats. And you can show it directly on the terminal like this. Me, personally, for the sake of this presentation, I didn't do that because it's very difficult to manipulate the output of that. What I did instead is to write it on some text file that I can load. Yeah, you can also profile by not adding the function on the profiler, but doing it that way, so with a decorator on either the functions or the methods of the class. So that's, if you prefer that way, that can be more convenient. So the point of me writing that on text is so I can show you this, which is a lot more convenient in the presentation. So I have, I can see the time, it's in nanoseconds. Yeah. You can see the time taken for the main function. It takes the total time. It takes 210 seconds, so that's not ideal. In main, we see that 98.8% of the time is spent on quicksort. So that is something nice, actually, because in the main function, I want the quicksort to do most of the work. So there is no point of the main function doing anything more than just that. So the quicksort itself, we can see here that we have 96% of the time spent on partition. It is something a bit personal, but when I do profile something, I consider that everything that is under 5% of the time is not worth considering, because you most certainly have other things that take a long time. So you need to focus on that first. So here we are going to focus exclusively on partition, because that's what takes like more than 95% of the time. On partition, I have different things. So I have that, the swap function, that takes a pretty long time, but it's only one line of code, so there is not much I can do at this point. The second most consuming line is the inner while loop. Then I have the first while loop, and then I have different bits. I have the incrementation here, so those shouldn't take 10% of the time. I mean, that's insane. The comparison here kind of takes a long time too. And what I want you to realize is that that comparison j below I appears 3 times actually. So if it's 3 times 8%, it's actually 3.3%. It's actually 25% of the time just for that comparison. That's a lot. That's way too much actually for something as simple as just comparing j for another integer value. So I might want to get rid of that at some point. That comparison, I'm pretty certain that I cannot do without it, because that's a crucial part of the algorithm, so I cannot remove it. But yeah, the incrementation, if I can remove it, it's nice. Otherwise, I mean, well, whatever. I would like to remove that, and I would certainly like to reduce the overhead induced by the loops here. Okay, so that's what I can say from this this analysis here. So how do I do that now? Please. I can do that well, from analysis to improvement. Here we move from the analysis part to the optimization part actually. I know what I need to focus and I want to do it intelligently. So first I'm going to focus on the algorithm, more precisely in the implementation of the algorithm. So I want to write faster code using fewer instructions. That's most often in Python. If you want to have faster code, just write fewer code and it works best. Not always, but sometimes, most of the time. So that is important. Remove all the slowest operations you can find. So the comparison, j and I, typically I want to remove that. And as said before, be sure that whatever you do, still sort your array, otherwise you will have an issue. So here is a better partition. So I don't know if you remember the first code. Before that. The first code looked like that, and now that's now it looks like that. So it's a lot shorter, and what we have is we don't have j anymore inside of the loop. We have it. Well, we do, but we have it here. So the implementation of j is done by the loop itself. So I don't need to care about that anymore. I don't have a comparison between j and I anymore at all. I mean, those 3 comparisons, they are all removed. So it should 25% of the time spent on that is just free now. We don't have it. So that's good. In the swap function is still there, but I cannot do without it. That comparison, again, I cannot really do without it. That implementation, I don't think I can do without it at this stage. And anyway, if it's only 1, I think it's okay. And it looks better. It should run better also. So yeah, that's what I said. So no more comparison, no more increments. I have only 1 loop, not 2. So that should run smoothly here. smoother, should run better. And I rewrite this function. It's basically a copy paste. I just change this because no, actually just change this and this. So I didn't change that because it was below 5% of the time. So and the main function that is also the same. So I have a better pixel, a better main, a better partition. That's good. So I use the same thing. You're going to see that a lot. I'm going to skip it pretty fast at some point, but so I think it's important that at least for this first presentation, have it. So I dump the stats on a file. I load that file afterward, and I analyze it. Here I write it on a text file. You can show it in the terminal with that comment. It's commented, and I have this. So now, what can we see here? You can see we can see that in main, still 98% of the time on better quick sorts. So I'm not going to spend some time on it. And on better quick sorts, still the partition is taking more than 95% of the time. On partition, I see that the for loop takes 22% of the time. That's kind of okay. 25% of the time spent on the comparison. I cannot really do with that. I can't do it. I can make it much more efficient. All of that takes 78 seconds. It's seconds, 8 seconds. 78 seconds for the partition. If we compare it with the previous one, the partition was taking 104 seconds. So we gained a lot of time actually. We gained the 25% I was talking about. We are pretty close to it. So yeah, we gain some time here just by changing the code. Nothing else than just changing the code. So that's the first step of pre-optimization, writing better code. Now, we cannot optimize further the implementation, but what we can optimize is a constant. So what is a constant when you code is basically the time it takes to perform one operation. Whatever the operation, if it is in constant time, for example, the swap operation is in constant time because whatever the size of the array, swapping two elements should take the same time, whatever the array. So this is a constant that I would like to optimize, especially its for function because it's called a lot of time. So that would be nice to optimize it. Here I'm going to introduce you with the JIT compiling, JIT compilation. So JIT stands for just in time. I'm going to talk a bit further on that later. So yeah, the idea here is to compile some reused functions. So Python is interpreted. This comes at a certain cost. So it means that while your code runs, the interpreter has to read a line of code, understand what it says, translate it into binary, and then run it so on the CPU. This takes some time. Of course, if your code is already in a lower representation binary, for example, or in something in between, it takes a shorter time to execute, so it should be faster. That's nice. So just-in-time compilation, yeah, that's what we're doing now. I'm going to do that with Numba. So Numba is a very nice library, if you don't know it. And I am going to do that explicitly. The latest versions of Numba, I think, do not even accept Python anymore. So here I just specify, okay, I don't want you to run Python, so you can go faster. So it's a bit weird to say, okay, I don't want you to run Python in Python code, but that's basically what we do here. So I don't freak out. I'll show you how it works. So Numba compiles Python functions and runs them at on a low-level virtual machine, LLVM. So it's not binary directly, but it's a very low-level language. So it's very close to binary, and it's pretty fast. It should be faster. So using Numba, I wrote it in blank here. You can use it like that, or you can write from Numba import it or something like that. So this is compiled just in time. What that means is that it is not compiled before. If I'm writing code, I run it. The first time it is encountered, Numba awakens and actually compile your code for you, and then runs your code, your lower level version of the code. So it should run faster. But there is some compilation, some compiling process happening at some point. You need to be aware of that. As I said, no Python goes through means that the function does not use Python objects. This is an issue for me because if you remember, my arrays are basically Python lists. So it removes the overhead induced by Python. That's why it's better to have Python objects. But array is a Python list, so that is an issue. That is an issue, but at the same time, what I'm doing here is using simple integer values. Using a full Python list is kind of an overkill, actually. I don't need that. It's way too powerful for what I'm doing. So it's a bit weird to introduce NumPy that way, but I mean, it's the best way I found from Nimba. NumPy is another library that is very, very, very famous in scientific computing. You mostly already have heard of it, or if not, well, no, you have. So it is coded in C, so it is compiled, and it is very low level. So it is NumPy is very, very highly optimized, and it is a nice library for you, so it's easy to use. It provides multi-dimensional arrays of primitive types. Primitive types are types that are easy to operate on a CPU. I mean, integer, floats, values. Strings are not primitive types because, but yeah, a character is. So the bits, the parts of the string are primitive types. I mean, that's booleans are primitive types. So yeah, that's what you use most likely all the time, numbers, because most of the time, I suppose, integers and float values. It is meant to be fast, and it is meant for numerical manipulation. So linear algebra, you can do that in NumPy, matrices, tensors are basically matrices in more than 2 dimensions. And it is, the term became really famous with TensorFlow. It is used either alone or with scipy. Scipy is another very nice library. Mathplotlib, if you want to do plots, you mostly have heard of it too if you need to do plots. TensorFlow for linear algebra and neural networks. PyTorch, the same, but on Facebook, not on Google. NumPy arrays are not considered as Python objects by Numba because inside they are not a list, they are not a variable size array of objects. They are actual arrays, lower level arrays. Numba loves NumPy, so it works. So when you look at the code here, I mean, I talked about NumPy, nothing changes. Okay, so that's nice. NumPy has a very nice interface that looks a lot like what you already know if you move from pure Python to NumPy. But what does change here is that I do not copy the lists anymore the same way as before, but I create an array that is basically a copy of the array that is a list. I create an array that is a NumPy array. You would notice here I specify the data type of the array. By default, it is a float 64. Here I just need integers, so I'm using 32. And I am using this. I'm using my quicksort algorithm. I still check that my array is sorted, of course. So that again, I will go through that. You know that by now. And what do I have now? I have this. So on the main, still the quicksort takes most of the time. On the quicksort, still partition takes most of the time. On the partition, I don't see much things that are different. I mean, this seems to be pretty equivalent. Actually, it's been worse if you remember the previous results. The partition was taking 78 seconds. This one takes 87 seconds. So that's not ideal. So I have something that should be faster. Should be, I hope it to be faster. It's actually slow. It's not. It doesn't make sense. So what's going on? The compiled version of SWAT did not speed up the process. That's an issue. The purpose of compiling SWAT was to make it faster. Is it possible that the compiled Python is slower? To inquire that, I made that test here. So I basically call 3 times swap on an array that is just 2 values. And I call faster swap, so the compiled version, on the same array, and I just swap 2 elements. And that's a bit stupid, but it serves its purpose. Again, you know that part of the code, so I won't go through that. And what do I see here? Well, this is most likely the reason why it was slower. So the 100% of the time, I mean, it's not 100%, but the rest is negligible, but it amounts to 100% of the time, is spent on the first fastest swap call. If you look at the time here, the first swap call actually takes longer, about 10 times longer than the second call. That is about the same of the third call of swap. So this is Python. This is not compiled. And here is the number version. So 6 times 10 it's going to 7 nanosec are spent on that. And that explains why actually faster swap seems to be slower. It's because the compiling process actually occurs here, and then I lose time actually. I lose time on the compiling, so it's apparently it's not worth it. So is it slower? It could be slower. It could because you have a flat cost and then you have faster thing. Okay. So and also under the hood, Python performs a JIT compilation. If you remember what I said earlier, Python reads each line of your code, translates it into binary, and then applies it on the CPU. Python is pretty smart. So if you use the same line of code several times, because in a loop, for example, it will not read the same line of code again. If you use a binary version, it has already compiled before. So Python does some sort of JIT, but on a line per line basis. It's not as advanced as Numba, but still it does something like that. So for swap, which is only one line of code, that's what happens here. So Python is better than Numba on that specific case. What's the point of using JIT with Numba? It is most only useful, and it is in this scenario. So here I compile another function, which is partition, and I use the fast swap inside of this compiled version. So what I do here is what we call inline. So I inline Numba swap inside of the Numba partition. I can do that because that is not Python anymore. That function is not a Python object. Now it is a Numba compiled function. So I can use it in another Numba compiled function. Just swap them work here. So I mean, here is a bet. I bet that this would be faster because there would be more than one line of code. So the Python built-in JIT should be slower than the Numba version bit. The rest of the code again is the same. I just use faster swap here instead of swap. The rest of the code is the same, and so I profile it. Okay, profile it. So you know that right now. And now what is pretty nice. I cannot. The profiler cannot know what happened inside of a compiled function. That's a bit, that's not a big deal, but you need to be aware of that. So I cannot have insights on what is going on inside because it is compiled. It's a block that Python has no insights. What Python cannot unbox it. But what I'm interested in here is, okay, the main I didn't care that much, is the time spent on the partition. Here it's 11 seconds. If I compare with what I had before, yeah, I mean, I don't need, if I really need to say any more than that, we moved from 87 seconds and 78 previously to 11 seconds. So the gain in time is just incredible here. And that is the whole point of it. Well, Numba is pretty cool. If you know how to use it, if you know where to use it, and this is the point here. So what I said before is true. So JIT is useful for easily used function. Partition is used all the time. I did not compile Quickswap to compile partition. Numba shines when inlining compiled functions. So when you have a complicated project with lots of functions, if you use compiled functions inside of compiled functions, there you have some gain in speed. If you use it for some very small functions that actually you can leave it that way, like swap, for example, then you will not gain anything. You will most probably lose some time. It was useful to compile swap, but to inline it inside of another function. That's the point of compiling swap. And in that, as always, in that, try both. I mean, it doesn't take much time to compile function. You just add a decorator on the function. So just try both versions and just test profile, compare them both together as I did here, and see which one is better. Okay. So well, we are getting the end of this part of the presentation. So I want to wrap up with this. So this is the kind of a whole thing of the different versions of the code I have had so far. I'm using cprofile to profile it and to produce some family picture. So same code as before. Show you this. So I said previously that the green does not mean it's good. It actually means between the deep blue and the red. So it's actually what takes the most time here. It's bright. Anyway, it's counterintuitive. Personally, it's actually yeah, I had to adapt that. but you can see the details here. So the bad student here is I know it doesn't look good here, but it's the better, faster quick swap. So the one that uses the faster swap, that is not compiled itself. As we might expect, this one is slower. Is the slowest. It uses the better, faster partition. It uses the fastest swap. And here we have the rest. But that one, oh, that's where actually that's a previous version of the picture. That's arrow here actually should be that way because I changed that afterward. That's an old picture. I don't know why the picture used that. I mean, what I say is about the same anyway. So you have, well, you have that graph. I mean, I like the picture because it shows you, okay, what's a profile can do on something a bit larger than just 2 or 3 functions. Because yeah, it's meant to be used at a larger scale. Imagine your full project with lots of code in every direction. That serves you a lot because you have some highlights on the plot. Okay, this is the points you should focus on first. Looking at the percentage, because that one takes 52% of the time. That's quite a lot. That's a lot. That's way too much. Oh, also, here you can also see that I use the built-in sort method of the list. I mean, re-implementing a quick sort is a bit stupid. To be honest, it serves its purpose when you want to showcase things, but actually when you want to code, you don't re-implement the sort function, especially not in Python. That doesn't make sense. So if you look at the sort method, it's here. It takes 0.74, 64. You can reach 6. It takes 0.64% of the time, so it's less than 1% of the time compared to whatever I do. So yeah, it's a lot faster. So you shouldn't re-implement that. So the sort method of a list is way faster than anything. So do not reinvent the wheel. I mean, that is something we heard so many times in computer science. Always ask yourself, is what you're doing already exists? If it is very useful, like sorting an array, for example, people mostly already have done it before. So don't do it yourself. Just use something that already exists. In other words, make a state of the art of the existing solutions. Worst case scenario, you lose some time looking for something that does not exist. It takes you maximum 2 hours. Best case scenario, you actually find something that can speed up your development a lot. So you should do that definitely. That is the best advice that I can give you at this stage. Is look for existing solutions. So we are at the end of this part of the presentation. If you have questions, I'm use. Otherwise, I think we can move to the other side. Yep.
Is there a way to quickly deactivate the profile so that you have your code running at low speed without the need to remove all the constructor?
That is exactly, yeah, actually, that's a very good question. This is exactly my point when I do, let's skip too far. Well, for C profile, you can launch it from the command line or from a Python script basically, but without altering your code at all. So if you don't use a profile, you don't alter the speed of your code because your code is not altered. But when you use a line profiler, if you use it that way, it shouldn't trigger. I mean, I don't like that way of doing things, so I don't use it personally, but it shouldn't trigger the line profiler. But what I do personally is that. So I do about the same thing as before. So I have another script that, well, you don't see it here because I don't need it, but you can import every function from your project, and then you just choose which function you want to profile, and then you run the main function. So this is another script. You don't alter your original code. So the question is not, can I deactivate? The question is, can I not activate it? And the answer to that is, okay, you just want to use a script, just use the main that exists, and the main function is here. So I can do the exact same thing than this without a profiler by just calling the main function. That's it. So that's I like it. I mean, that way over that version where I actually have to modify my own code. So yeah. Other questions? Yep.
So it's very several times like for loop
Ah, okay. I mean, Okay, I think an example. This, right? Okay, see, this actually, you can do that in Python, and it's used most of the time when you say that you don't care about the return value. So I can do underscore equal something. It means I don't care about what is returned. I just want to do it. For example, in a for loop, I need to put something in here. Okay, I don't care I could have written for I in range, but I don't care about I because I don't use it elsewhere. So just saying, okay, that's that amount of time, and whatever happens, I don't care about that. So it just you can. I mean, this is more question of style than of any use. So yeah, don't be confused by that. It's nothing. So and when you're in the interpreter, by default, this is the last value returned. So if you type something, you want to recover what was last that wasn't stored in some variable. Actually, this you can reuse it that way. So that's like the nth part of on a simple calculator. If you're familiar with it. Other question? I don't know what time it is. Oh, okay, I talked on it actually. I talked on more than expected. No, it was fine. Start. Okay. So I leave the talk to you. Yeah. Yeah, it will be kind of. So now, as I said at the beginning, we are going to do some kind of exercise to. If you open the PDF from the Indico website, the one called part 2, okay. So this one. Yeah, it was just to show you. You will find so the first slide on that on this second part, it will ask you to follow these steps in order to do an exercise in which we will test C profile and line profiler for an example code that it's there. So you have to connect to any of the SESI clusters. So you can connect the one. So I guess at this point everybody should be able to connect and work on a cluster, edit the files. So from any of the SESI clusters, you can recover that. Is the terminal on? And this will be available. Okay. So this.
So on link file, I see the directory on the screen. It's this. Maybe it's best to follow to work on the file.
It's not sync. Okay. So yeah. So it seems yeah. So this is a folder on the common storage to all the clusters, but it seems that to be not in sync, at least with Lemaitre 3. So
it's also
yeah.
So I don't know. Yeah, I copied that from numpy, so yeah, I didn't check yesterday, so I didn't.
The bottom line is
Yeah. So then, yeah, connect yourself to numpy because it seems that only from there, yeah, because of that technical issue, only from there we have the the correct folder. So then connect it on NIC5, you recover that somewhere in your home. So what? Because I added the link. So yeah, after recovery, we go to exercises and you have the README that will guide you on what you're supposed to do. So you have, so the first thing is to load all the modules that you will need in order to have Python in your environment, line profiler also. As Nicolas said, cprofile is part of the standard Python library, but that's not the case for line profiler. So it's a different external Python extension, and there's a specific module for it. And then we load also mathplotlib because the example, so here, as mentioned in the slide, the example is a Python implementation solving the two-dimensional diffusion equation. You click on the PDF, you should open your browser. So the piece of code is basically the one shown here in this example, but we organize a bit in order to have a different structure. So this is the code that the README asks you to work on. So it's the same implementation as shown in that tutorial, in that website. It's also the link I mentioned there. So you have all the details of the math behind, but what we are doing, we are solving a differential equation of a function depending on two spatial coordinates, which evolves in time. And this function for a given pair of coordinates, it will give me the value of the temperature on that part of the space. So it will represent, in this case, it will represent a hot metal plate. And then the initial condition set in the examples. So this hot metal plate is, it has a given, let's say, cold temperature so the initial condition at time 0, it will have a cold temperature on the whole plate, except for a hot area in the center that it will be a circle at a given defined hot temperature. And then the code will solve that equation to model how this hot area will diffuse along the plate. So yeah, there you have the detail, small detail of the model and the and how to discretize that PDE and then to allow that the implementation to solve it numerically. But we won't go to on the details. The important thing is that you have in this code that we are the exercise is asking you to work on. We have a main function where we define all the parameters that we need in order to create the model, and then the main will call what is called the initialize function that will create the initial discrete representation of my U function. It will set all the initial. It will set all the values for this discrete representation of the function for time 0. So it will return me a grid representing with a discrete representation of the function at time 0. And then the main will call the integrate function, where they are the main. We have, of course, to provide them the function and for different parameters, but also the amount of integration steps. So the first parameter defined here in the main is the amount of integration steps. So how much time steps I want to integrate, I want to make evolve my problem. So it will call integrate, and then integrate. It will do the actual integration, but so it will define extra parameters I need to do to solve numerically the differential equation, and then it will call many times. So for each time step, it will call the specific function that does. It's called do time step. So it's a specific function that does each increase of time step. So you have a main calling two functions, and then one of the functions integrate, calling another one. So it's exactly what is on this tutorial provided here, except that instead of being just a single piece of Python code, I made these three functions in order to be able to use the tools that Nicolas presented. So in the README, you have the instructions in order. So the first you use C profile. So the step one, it's a reminder of how would you run this for a given code and output the output of running C profiling on that code to a given file that we call, in that example, it's called my output file.stats, but you can name it as you wish, of course. And then the second step, there you actually have a step-by-step description of how you load this file. So on an interactive Python shell, how you load that stats file that you outputted with the C profile, and then how you print this result. As Nicolas said, he used pandas to print that, to format it for the slide presentation, but you are not, it's not mandatory to use that. And the important thing is then to is the link here to the documentation of pstats, because here we are using some specific methods with options and arguments given to some methods, and in the documentation you will find all the different kind of options that you have for these methods in order to sort the stats in different ways. So of course, there is written for a generic thing like my code, my output. But the goal is that you run that for the diffusion 2D.py. And sort it that way as shown. It should list you the most time-consuming function at the beginning. Of course, yeah, from this kind of code, you could infer from looking at it where you will spend most of the time. But yeah, the goal is that you experiment with it. So I know everybody's connected to NumPy. Yeah, okay. And yeah, there is actually, yeah, that's why we are. And yeah, why we import mathplotlib. So here it's commented, but part of the code provided on the tutorial, it will also, it has also, yeah, the code to create a plot of different snapshots of the state of the grid at different time steps. So the way it's encoded, it will create a snapshot for this 4 moments. So at time 0, at a quarter of your time, the amount of time steps, so quarter of time is 1, at half of time, and yeah, at 1 step before the end. The -1 is because, yeah, in this Python loop, it will actually go from 0 to n steps -1. Because of how the range function will create that iterator. And so here is commented because we are running it yeah, on the cluster from the terminal. But in case in your computer, in your environment, you have NumPy and mathplotlib available, you can uncomment that, and you should get plotted by mathplotlib a plot like that. But yeah, that's the reason of importing mathplotlib, of loading the mathplotlib module, to avoid having an error of, yeah, I could have removed that function, but I prefer to keep it, so in case of, I wonder if we connect with by the way, if you run the code as is, it yeah. It will already, if you check in the integrate function, the code is measuring the time spent on it. If you check in the code, yes, it will work on what I'm showing them. The integrate function has a, yeah, it returns the runtime spent on it. And I wonder if Try to basically. Yeah, no, well, yeah, forwarding X is not enough for mathplotlib.
The great exercise and help for questions.
What modular package provides gplot.
Provides what?
Gplot.
I don't think it's installed on the cluster, but I mean, what I do is that I copy the stats from the cluster on my personal machine, and then I have it installed on my machines. That's something that wasn't actually on site.
Okay. Yeah, in this case for the tutorial we don't. For what we ask to do with a line profiler, you actually don't need that.
I know it's possible.
Yeah.
I don't know.
Yeah, but it's a package on its own.
It's part of the.
No, I just keep installed gplot.
Oh,
So yeah, it's what you have to do. Okay, yeah, okay, yeah, of course, because yeah, you could generate that. Yeah, one thing that if you are going to be doing profiling, as Nicolas mentioned, that at the beginning, that you will you will actually try to get a reduce. Doing the profiling adds a lot of overhead, especially line profiler. So when you run line profiler on a given function, it will take in between 50 to 100 times more to be run than if you run without profiling at all. So in principle, actually, this kind of tools, ideally, you will set it up in your machine. And you will do that. The idea is on the cluster, you will already run, say, what we can call production code. And then especially for this kind of tools that will show different plots, it's better to have a dynamic environment in your machine to get the plots being shown. Okay, so here I just copied as I was. I copied the file from the cluster to the local machine of Nicolas and commented the plot part. So this is integration up to 500 time steps, which is 300 milliseconds using with all the units that we gave to the parameters. And you can check if we, for instance, increase that to we should see a colder plate to integrate even more, a colder final plate, so darker. Yeah. Well, I didn't get both plots. Yeah. So here you see here I integrated 3,000 time steps. So you see the final result. The example shown on the website is only 100 time steps. So you see what probably up to 60 milliseconds. The middle is of course quite hotter than if we let that evolve. So the modeling here is that we start with that hot area, but there's no source to keep heat in that hot area. So it will diffuse and eventually everything we get to the core temperature. So was someone able to list what you got for the it's for the first part. Okay, so we will do it. So if you print the full stats without any sort of filter at all, you will get a huge list of all the with a lot of the built-in methods. Okay, well, probably you have a huge list of a lot of internal codes to build in the Python method, so it's not. So that's the reason, yeah, why we ask. To apply a filter like that to sort by time, we sort by runtime, and then we filter. Here you can put a regex, a regular expression to match the different functions. And so we put diffusion asterisk. It will filter out all functions that that are really part of our code. And yeah, of course, we see that where we spend most of the time is the do time step. Yeah, it's not surprising that we are calling this 501, which is the amount of time steps. And yeah, there is where we spend most of the time. So the second part of the hands-on of this exercise asks you to for the most time-consuming function, so the do time step, to do a line-by-line profiler, a line-by-line profile with the line profiler. And yeah, but I will move on. I will just run the. If we want, well, step 3, it mentions how you can fast run the line profiler to profile a function. So in that case, you need to modify your code. You just add a profile decorator. To the time step. And then you use this tool, which is part of the line profiler extension. But then on step 4, we don't go into all the detail of that. You can do it on your own later. It points to a slide in the presentation where Nicolas showed how to create an extra script that will import your code. And then on that extra script, you select the function that you want to provide. So that way you don't modify your original code. Here we modified it, but the modification was just adding the add profile decorator to the function for which we want to see all the details. Yeah, and then we get the output with the line-by-line profiler for the time steps. And then, yeah, well, we see that here we have this double loop double loop through all the domain of my U function. And then, yeah, of course, we spent most of the time, so almost 100 or 90-something% of the time executing the 3 function on the inner loop. The 3, sorry, multiplications and additions that are on the inner loop. So the step 4, then you can look on your own. Yeah. Yeah, okay, and we can copy, yeah. So actually we copy. I will copy it to the. Yeah, let's say the solution for the 4 is in. Yeah, let's copy. HPC. Yeah, well, there's a permission issue that it's a folder owns. Yeah, it doesn't have right group permission. Can you, Damian? Can you add? Can you make 755? 775. No, but what? No, yeah, but you're on the sysadmin group, so you should be able to change it. Wait, even otherwise I do it. Yeah. Okay. Yeah. Okay. So for the 4 now on the folder where you got, actually you can read also this, but now on the folder where mentioned on the slide, you have the solution for, so let's say the final. How would you call without modifying the original code? How do you write a script in which you actually import? Of course, this script must be on the same, to work it that way, must be on the same folder where you have the diffusion 2d.py. So you import all functions from there, then you import line profiler, and then you can select which are the functions that you want to profile line by line. And you dump the stats to a given file. So you have there the script which was asked to do, and then I will just before we go on with the compiling with the Python binding and how to compile Python, how to bind the Python to compile code. I will just mention what we can test it before. I will load Numba, which was already introduced by Nicolas. And then as you saw, well, if I run it directly here in the cluster, yeah, so I have to remove the. So what I mentioned before is that the integrate function, which is the one where I spend most of the time calling do time step, the amount of time step, it has, so it has this, we record this variable before entering the loop, and then it will return the time period, the time interval between entering and exiting the function, before entering the loop and exiting the function. So the time spent integrating, if we run it directly here, yeah, I ran it before, but just taking like 14 seconds. Yeah, about 14 seconds for 500 time step. So now on the code, I will just to show how this just-in-time compiling thing works. Okay, Nicolas showed, but here we show it interactively, live. So I imported number, and then we know that here is where, yeah, the function that is called 500 times, where I spend most of the time, and so we have our sorry that Python equal true. So we add this decorator, which what we'll do when I executed it now, it will just in time. So when the code begins to be executed, it will compile that code. So the numpy extension, it will compile that function, create in memory a binary version of that function, and then the code itself, when it runs, it will execute this binary, this binary object of this function, instead of being Python executing that thing all the time. So you saw that we just added the decorator, and then if I execute this with the numbers just in time compiling, yeah, we went from 40 seconds to 0.4. Of course, it's quite impressive because that function is really the most inefficient that we can do. It's a double for loop being done by Python, so by the Python interpreter. If we are using but the numpy library, so here U is a numpy array, so the grid, the discrete representation of my function, it's a numpy array. And then numpy has methods to avoid to loop through a numpy array, avoiding to have to do a Python loop. It's mentioned actually on here on the explanation of the tutorial from where we got this. So the problem we were working on, it has this, it's like the direct literal approach of writing this this loop that I have to do to update my U function in time. But it mentions here that this is extremely slow. And then in the code here, it shows how you would do that instead using the what is called for numpy arrays indexing. So you have methods for a numpy array which will allow you to loop through the array and update its values. So basically, that double Python loop can be changed by this single line, where we do the loop actually on the x coordinate and y coordinate of the U function. And then if we the code that you have, that you had here, the what called NP indexing. It is exactly the same code. It's just changing in the do times 10 function the double Python loop by the example shown on the tutorial. And then if we run that, you see by doing that, it's running even an order of magnitude of even. So this is 0.4 and this is 0.04. So the trick is that there you can then do the line by line profiler, and the trick is that there when I do this in this one line using the array indexes of NumPy, I'm running fully on the, let's say, on the binary library of NumPy. It's not Python, so Python just hits that line and then all the loop is happening inside by methods which are part of a binary library. So anyway, maybe for some fast, so Numba, well, you can see the usefulness of Numba, but then you always have to take care of if you are using already an external, especially NumPy, which has a lot of methods for doing a lot of things. Before you go for using Numba to optimize some part of the algorithm, you have to really read the documentation of NumPy and exploit it as a maximum. Okay, so now we will go actually back to the presentation and discuss a little bit of. I will show a couple of examples of. It will be just to illustrate how do we actually create a Python extension. So what's called Python binding, which is an interface from Python to a compiled library. So here is just mentioning some of the features of the NumPy library. Well, it's a library providing, especially mainly not only, but a lot of linear algebra methods to operate among arrays. It also provides a new object, the array data type, in which we have we can create objects that they look like lists when printed, but the representation is completely different from a Python list. So the NumPy array, it has all the objects, they have a defined data type, they are integer floats, 32-bit floats or 64-bit floats. They are stored in memory like you would store in memory a C array. So in a contiguous a NumPy array, it will be stored in a contiguous part of the memory. So then when you access the different, you are particularly looping through an array, you are moving to contiguous memory addresses, and for anything that link to doing then mathematical operations through these elements, it will be way more efficient than doing that on a Python list. So here, is a link to the slice indexes that we show how that would work for replacing a double loop in this diffusion to the example. And so the NumPy library is an example of what we call Python binding. So it's a library consisting of compile C, mainly C and Fortran code. And then from Python, we can access those libraries. We can create objects and access their methods. But in order to create that, we have, there are, let's say, two main approaches. If I have my Python code and I want a part of it, instead of using like just-in-time compiling, I want to provide a real binary of that, and then yeah, a method to call that library. I will have to port my original Python code to the most similar thing is using Cython. It will produce some kind of Cython code, which is a kind of a mixing between Python and C. Or if I already have, if there's already an existing C library, Fortran or C++ that does solving some kind of numerical methods that I want to use from my Python code, I can create a wrapper, an interface to these already existing libraries. So compiling Python, we have the option, what is called just-in-time compiling is what that Nicolas presented, is a numpy and that we saw in the example, that we will, on the fly, live compile something stored in memory. But so every time that I run my code, it will do this pre-compilation live. And then, of course, if I'm calling that a lot of time, I will have a time gain. But then I have another approach is called sometimes ahead of time compiler. So I have my piece of code, I will compile it once. I will produce a binary library, so a .so object that I can then import from my Python code. That's how numpy, scipy, and anyway, TensorFlow, PyTorch, all those kind of library are a piece of code, C or C++, Fortran, that it's compiled and then called from Python. So we will show, I will show an example using Cython to produce a Python-like code. To produce a binary library for solving to provide me a method to give me the n Fibonacci number from the Fibonacci series. So the Fibonacci series, I guess everybody heard about it. So it's defined as a recurrence. So the nth number is given by the addition of the two previous one, and it's defined that the element number 0 is 0 and the element number 1 is 1, and then with that recurrence relation, I can create the full list. So this is how I would create, how I would in a pure Python code create this, define this recurrent relation, and then I could call in that function. I can print, in this case, the Fibonacci number 15, and then so as I said, here is just to illustrate how do we, for instance, if we have if this is initially my Python code and I want to, so here we are not going to have speed gains with the values that we are taking as example, but it's how a piece of Python code could be transformed into a binary library. So if we use, for instance, Cython, we will, so this function, we have to, what's called Cythonize it sometimes. So we have to, so you see here is exactly the same code that we have, and we are just defining the data type. So it looks a bit like C thing. Here we define the only thing that we did is to define the data type in this case. For more complex situation, I have way more. It's a new language, so it's not only just defining data type using writing Cython code. But for this case, it's just enough that, because then I have just additions as operation and a loop. And then if I encode this in a file, for instance, called like that, fibolib.pyx. So here is mentioned that all these examples, you already have them. They were in the examples folder of the folder that you copy for the hands-on. So in order to, as I said, we have to compile this. In order to compile it, we need to an equivalent of a kind of makefile. It's usually called setup.py on Python projects. So if I create this Cython code, we name it like that, the setup.py, it will it would be something like that, but it would be precisely that. And then, in order to build the library locally there, not to install it in your Python, in your global Python path, but just to build the binary object locally where you will have your Python code, you execute the setup.py with those options. You will see that on the directory where you run that, you obtain a binary object. It's called fibolib and stuff.so at the end. And then on that same folder, you can write then a Python code, which would, from that library that you generated, you import the Fibonacci function. This is the only one that we have on this library. And then you ask to print the number 15. So I will show the example live just for this case, and then I will. Let's say you already have this. So you see here we have the Cython code, the setup.py mentioned on the slide. Setup.py, build an external extension in place. You see we obtained, so it actually produced some C code that it will compile. Here is temporary build objects, and then this is an important thing. Actually, these two, you can delete them. So this is your binary library of your Cython code, which it has only a single function. But you see then my code now is just from fibolib, importing Fibonacci and printing the 15, and then we run it, then we get the output of the 15th Fibonacci number. So also Cython allows, as I said before, not only allows to write Cython code and compile it and then create the binding to use it from Python, but also if you have already a C code, here I won't run it, but it's mentioned here that you look in Fibo wrapper to see. So here you see that what we have is a real C code. This is just pure C code. And you can, if you follow, if you use the makefile, if you follow these steps, you will also produce a binary library that you can call them from Python. So that I let you to experiment. And then just, the final example is how, if we want to create also a binding or an interface to an already existing Fortran code, we can use the F2Py tool. That is used a lot. It's part of the NumPy project, and it's used a lot even for NumPy project to compile Fortran code used by NumPy. And the F2Py tool, it's some kind more straightforward. You don't. You can write a makefile, but for, let's say, simple example, it would work just if you want to. You can, for something very simple, you don't even need a setup.py. So with F2Py, if I have a Fortran function like this, it's an implementation of the Fibonacci. One possibility to code in Fortran how to get the nth number of the Fibonacci series. You produce your module, your Python module, or your binary library like that. And then again, your Python code, which, if you produce it that way, it must be on the same folder as the obtained binary library. You can just run it. Let's see one is. So here I have my pure Fortran function, and again my Fibonacci.py is the same. I import fibolib. So if we run this, the same. You see, yeah, it will port that to Fortran and then compile with Fortran. And here, yeah, the result, yeah, it doesn't keep the temporary Fortran code. As output, I have just my binary, and then for my Fibonacci code is also importing. Well, here, yeah, it's just I'm importing the full library, which only have which only has the Fibonacci function, and yeah, and so that was what we had to say about the Python bindings, and then there are many other different tools if you want to produce interfaces to C++ code. There, well, Nicolas worked a lot with the Boost library, and then you have PyBint 11. But anyway, if you Google like Python bindings C++, then you will find the options. It's just to know, the idea was to show with a very simple example how these things are built. Yeah, that's it for this part. So now we yes, so yes.
Just explain how to like build a user. Previously we can see code like
Okay, well, we can show. I didn't run it, but it was here. Yeah, the slide. So in this case, in this case, we have. As I say, this is pure C. The header is just defining the data type. But this is a pure C code. And then, yeah, that's what they say that F2Py is a bit more. Here we have to, in Cython, write what's called the wrapper to this C library. And then my ctap.py. Yeah, well, we need to define a couple of different things. So we provide the Cython code and the C code. And then with all these bricks built, yeah, I have a make file here that will do, so make all, it will execute the setup.py to build the extension in place. And the same thing, it produces here a binary library, which is already it produced my extension called grab cfib, from where I import the cfib function there. But then if I execute that, also just to this that I'm not cheating, let's change to 22 to see that. But yeah. So that would be an option to create it's called a wrapper, but yeah, they are all Python buildings. Okay. So well, now we can move to the final part. Where Nicolas is going to present how to do parallel programming from Python in particular. Well, okay.
I don't know if someone needs to go to the bathroom.
Okay, yeah.
C'est les réunions aux États-Unis parce qu'apparemment il y a d'autres gens qui sont pas là.
Ah oui, okay.
Donc en fait on est chez
Ah, Moi, ouais, ouais.
Non, mais c'est pas le problème.
Mais après, la discussion, on a dit que
donc c'est récent. Ça, il y a eu 15 800 gigas sur le web de taille gigas. Donc ça a bloqué les serveurs, c'est la part de et donc, on va avancer le détail. Ça peut bien vérifier chez moi, je vais vérifier.
Nicolas vient de la ville, donc Raphaël. Nicolas, Raphaël. Donc, Raphaël a rapporté mais on va, sinon on va, en fait, moi, j'avais amené un sandwich. Oui, ici, à la gare.
Ça, vous n'avez pas d'explication aussi.
Pas sans sandwich.
C'est un bon point. J'ai vu quelqu'un qui a un table encore plus beau. Et il n'est pas ici, mais alors, y compris là. J'ai l'impression de découvrir à quelques lignes. Je t'assure, alors, ouais. Et alors, ce qui est chiant, c'est que tu as vu aussi peut-être que donc, c'est rouge et tu as des parce que ça se constitue. Alors, ils ont dit de 4, c'est jaune, le 4 est rouge, et bien, on voit, il suit comme un grand. De fois, j'ai écrit, en fait, et même au lieu de dire. Ça casse-couille.
Mais normalement, il y a aussi votre carré. Non, il fonctionne très bien sur Linux. C'est la machine de madame.
Ouais, donc, oui.
C'est unique. C'est une vidéo. Parfois, il faut pas le multi-écran. Non, oui, non, la machine, en fait, c'est lui. Si de temps en temps, il faut qu'elle réponde, obligé de brancher un écran externe pour avoir normalement, il doit rester c'est le truc qui m'a donné, j'ai acheté ce changement de date. J'ai pris un info. Je n'avais pas. J'ai racheté un instrument.
Il y a un port SATA et un port NPI. Tu peux maintenant mettre aussi un PC Express M2, un PC M2 pour mettre une carte SIM. Donc, en fait, c'est une carte cachée. Donc, je n'ai pas besoin. Je vais commander un après comme ça. Si j'avais pas de boot, sur deux différents Windows Linux sur le SATA et Windows sur le micro. J'ai poussé la RAM à, je crois, 32 Go. Celui-là, oui, et tu commences à lancer beaucoup de VSP. Ouais, donc on met du temps avec. Franchement, le processeur, j'ai une boîte. Moi, j'ai besoin de ça pour curieux. Oui, j'adore les gadgets. C'est sur Amazon, c'est ça. Square, un truc comme ça. Site, je sais plus comment ça s'appelle. C'est une cherche. On a des petits comme ça, de 2 mètres et 3 mètres. Et ça, c'est everyday, on est ici. Ça me reste beaucoup.
On a 50 minutes. C'est midi et demi. Midi et demi. Ouais.
De toute façon,
mais là, j'ai beaucoup de slides. Beaucoup de slides, il y a des trucs que je vais skip.
je ne te presse pas. C'est pas dur à attendre.
Okay, so we'll start again here. Okay, so for this last part of today's session, I'm going to talk about parallel code. So one way of making your Python code faster is to make it faster the different ways we already saw. But you can also have parallel execution. I mean, it's pretty obvious that if you have some code running at the same time, it should go faster. That's the point of this lecture. I am going to take some freedom here about what we usually call parallel in computer science. I am also going to talk about vectorization because to me this is some sort of parallelization that is it's not parallel execution, but still that's very interesting. Again, I'm going to use a type problem here that is simple enough to show you some things, but complex enough so that I can actually show you something. So here I chose a matrix multiplication. So I don't know if you're all familiar with it. It's pretty simple as math goes. This is the math behind it. This is the algorithm behind it. So there are more than one algorithm to do that, but this is the mathematical correct way to do it. So the idea is pretty simple. I want to compute the matrix multiplication of two matrices, A and B. So they have the shapes. The shape is never going to change. So matrix A is shape m times L. So I have m lines and L columns. B is shape L times n. So L lines and n columns. And C is shape m times n. Each element is basically the sum of the product of all elements of the one line of A and one column of B. Visually speaking, it's exactly like this GIF that I also took from I'm not sure where it was, but somewhere in the internet. So the idea is that I just iterate if matrix A is the red one and matrix B is the blue one. I just go line by line on the B matrix and column by column on the line by line on the A matrix and column by column on the B matrix to build each single element of the C matrix that is the green. So I do two things. I multiply element-wise, so that's the second step, and I reduce using a sum. So that's the two types of operation used 95% of the time when we deal with multi-dimensional array. It's element-wise operation and reduction operations. Say 95. So here for the element Cij, I take the ith row of A and jth column of B. Again, that should be straightforward. If you're a bit lost, I mean, the important thing here is not the algorithm, it's what I do with it. So now that the algorithm is in 3 steps, very simple. Now that we know the algorithm, I will have some code example. As before, the first implementation is not the best one, of course. So 2 steps basically. That first function that computes one element of the matrix C. So for Cij, I have 1 row of A and 1 column of B. And here I have the size of those 2 vectors. At this stage they are vectors, only 1 dimension. And for Cij, I iterate over L using K. And I just take the kth element of the row from A, of the ith row of A, and the kth element of the jth row of B. Okay, so this is element-wise multiplication, and then I just agglomerate all of that by summing them together into Cij. Okay, so this is what I just showed here. This is literally a translation of that in code. So I reduce with a sum, and this is for 1 element. Of course, I need to do that on for all elements. So for I in range n, for j in range n, and I do that for all elements of the matrix. Yes, I'm using numpy arrays here. I don't want to bother with lists or anything. You know a little bit of numpy right now. That is important. I mean, all the assert clauses I have all are commented, so they don't impact the performances of all profiling work I'm doing afterward. So you will see that often everywhere in my code. I cannot advise you enough to use that. You should check the code. Python is easy code. You just type assert and then something that should be true. If it's not true, then then your code is probably not working as expected. Here I know that the L and the second axis of my A matrix and the first axis of my B matrix should be the same size. So that's what I'm doing here. These two should be the same. I say that here it's pretty simple, but when you deal with n-dimensional arrays, it's easy to confuse the shapes. And most of the time, when something is wrong, you can see it just by the shapes. So this is very, very easy to check. First implementation, I suppose you guess it's probably a bad implementation, but we will see how it's a bad one. Again, as before, I want to have some test data, some benchmark here. Small difference than before. If you remember, I said, okay, I want to have something that is general enough. Here, I'm having another approach. I want 2 things, 2 types of benchmark. The first one, I want to have a low value of L. So you see here, you see the matrix, the produced matrices here. I have N, N, and L. So L here is pretty small. It's 10 compared to 200 and 400. While here, L is pretty high compared to those 2. You will understand why I do that later, but I have two cases I want to investigate. The driver program, well, I duplicate the main function. The reason why I copy paste that basically is that I have 2 different names for the main function, so I can separate them on the profiler. This is pretty ugly code because it's literally a copy of it. You shouldn't do that on actual code, but for profiling code, we don't care much, just to have different name on the profiler. And I have 1 main function that basically just calls those 2. Okay, I'm doing this here. I won't do the whole process again because it's always the same thing, and I think you're becoming to be familiar with the process of writing code to profile things with the first station. This again, now you should be familiar with that. I am going to use only line profiler because the project is modeled by just 2 functions. I won't use cprofile here. I think it's kind of a bit overkill. And I'm doing something that I wasn't doing before. I'm doing this. This is to call the main function alone. The reason why I do that is to ensure that everything that is JIT related is triggered already. So when I actually profile things, I don't have the overhead of JIT compiling or anything. This is like the cold start. the dry shape of my cocktail if you an initiate. So the idea here is I don't have it. That the cheats. Okay, if it is compiled, then it runs fast. If it's not compiled, then it's still going to run fast on a line by line basis because of the Python interpreter. So that's what I'm doing here. Okay, I dump stats and I examine them that way. So this is my first profiling results. I see that for the what's that? Okay, we discovered things on my computer. It's amazing. So I see that on my main functions, I have 99.9% of the time spent on that. So I have, I know where I should look for performances. Aside from that, I just look here. I have also 99.9% of the time that is spent on here, which is a pretty good thing actually, because this is the only place in the code where some computations actually happen. So the rest of it shouldn't take too long compared to that. So I'm looking inside of here. I have 3 lines of code that take all the time. So the for loop, okay, well, I'm just iterating over the different ends. The multiplication takes 50% of the time itself. It's way too much. That shouldn't take that long. But I don't want it to take that long. And 30% of the time is taken by the sum. So those are very simple operations. I don't want them to take that long. Seems to be a bit too much. And I mean, also the time. I mean, the time I spent on that is just too much. It's 5 minutes, more than 5 minutes. So yeah, that's too much. That's way too much. So how do I do that? Sorry. So I start with the first a technique that is going to serve you pretty well if you know how to use it. It is array programming. So array programming is a new paradigm that you need to get accustomed to. So here the atoms of what I manipulate basically of the atoms of my program are no longer variables in single integers. They are full arrays. So I won't use the Cij element, for example. I will use a part of C, like 1 row or 1 column of C. 1 row of 8, that makes a lot of sense. 1 column of B as a whole, not every independent element of it. So you apply operation directly on entire arrays. You no longer do it on a per element basis. So you may, I mean, take some time to move from thinking element by element to thinking into arrays. If you feel good with it, it's nice. Some people take some more time to listen to it. It's normal. It gets easier with time. The expected effects of that is that it should reduce the loops overhead, because if I work on arrays, I don't need to iterate over them. So every loops should disappear. Some loops at least should disappear. It relies on highly optimized subroutines. I mentioned what we more than mentioned NumPy several times. NumPy is compiled. You see some parts of NumPy are unfortunate too. It's compiled is done by people that know what they are doing, and it's very, very, very highly optimized. And it is in some nice packages for you. So you just import NumPy or whatever, anything else. You just use it basically, and you have all that expertise for free. It's for you to use. And another side effect on that is that the Python code remains high level. Python is meant to be high level. If you start to dive a bit too deep into the details of the machine with Python, then probably Python is not the language you need. So you want to stay at a pretty high level, so you can focus on what you're doing. You can focus on math. You can focus on those things. Every detail should be done by something else. That is Python. So here is an example of my function. So as you can see, the for loop is removed, and I have two operations basically: multiplication here and a sum here. Can be more. So here I have those two basic types of basic operations: the element-wise operation and the reduction operation. As I said, normal loops. I don't need to use L anymore because L is part of the type of the array. I use A row and B row directly. But again, don't mess the shapes of your array. That's really important. And I use NumPy. I use the reduction version of NumPy. Here is the sum of the result of all the things like the product, the max, min, standard variation, probably a lot more. And I work in, well, here I am in one dimension because one row and one column is just one vector chunk, so it's one dimension. If I am in n dimensions, I can choose on which axis the reduction is performed on, or I can reduce everything together. We will see examples of that later. So, I mean, here the code doesn't change. Anyway, that was the line where Cij was 90 something percent. The rest was negligible, so I don't need to optimize that now. And we can see, if I compare with this, I just look at the main function. I was at 700 seconds. Here I am at, where is it? Where's my name? I lost my, that's here. Here we are at 40 seconds. Okay, so the gain speed is pretty huge. And what I did is just change some ugly code by those 2 lines of code. And it seems pretty easy, right? Just multiplication, reduction with the sum, very easy. So this is pretty neat. This is the kind of speed up we like. So our programming, this seems simple enough, basically. Just you remove a loop, you multiply, you sum, that's it. And now my question is, can we go one step further? Can we remove all loops? Because what didn't change is that. So can we change the approach completely and remove all loops that exist? So the answer is yes. There are different ways to do it. I'm going to present you 2 of them. The first one is indexing, and the second one is broadcasting. Okay. Indexing is easier, but we will see there are some issues with it in this specific example. There is another one I'm going to mention, but I won't go further in that. On there is masking. So if you're interested, just check that out. It's pretty useful too. So for indexing, I want to remove the loops, right? So I said also that the spoiler alert, this is not a nice thing to do. So if you are familiar with NumPy and you see that, don't freak out. I know what I shouldn't do, and I know I shouldn't do that. I want to remove the loops, and I said I want to use arrays as the atoms of my program. So that's what I'm going to do. If I have 2 loops, I and j are integers, here I'm going to make it arrays. Okay, so I have an array I that contains indices from 0 to n-1, 0, 1, so on. I do the same for j with n-1, but I don't want just I and j, I want pairs of indices. So I want Cij where I is 0, 0, 0, and j is 0, 1, 2, and so on in all directions. So I want to repeat the I a certain number of times, n times actually. So I have n zeros followed by n ones, followed by n twos, and so on. And for the j, I do kind of the same, but differently. So I tile them instead of repeating them. So I just have the same array. It is just concatenated one after the others. 0, 1, 2, 0, 1, 2, 0, 1, 2, n times. Okay. Doing that, well, I build my C, it's an empty matrix of size n, and then I just collect the rows, saying, okay, now you give me all the rows that are at index I. And the 2 dots here is just to say, okay, whatever is a row, you give me that. Okay, I just want those rows, and I mean, I don't even care about the dimensions of what comes after. And I do the same for the columns here, except that here is on second axis, of course. I take it because I want the columns, not the rows. So again, I commented out the assert clauses, but if you can look at the shapes, I have m times n, because I is n times n indices, j also. I have n times n L shape for the A rows, and B calls is basically the same, but inverted. So I take the transpose of this. So this is the NumPy way of saying, okay, I give the transpose of that big matrix. I multiply them together, and I sum on the second axis, because the second axis would be L. Okay, so I want to sum that on L. So I have just m times n values, and those are my Cij values. Okay, so it's pretty nice because when you look at that, it looks a lot like the math. it's Cij equals the sum of, I can literally, on top of that, I can literally just draw a big sigma and read that. That's literally a translation of the math. So very nice, but there are some issues with that. So if we look at, that's why here the low values of L and high values of L become interesting. If I look at the low values of L, it takes 7 times 10 exponent 6, 7, 6, okay? And here I have 4, 7, okay? So, okay, if I compare with what I had previously, I already forgot, okay, 6, 7, 6, here, where are they? Here I have 4, 8, okay, so we are faster, we're a lot faster actually. If I look here, 2, 7, I think it's, yeah, we are actually twice slower. So it's a bit weird because we have a huge speed up here, but we are actually slower here. And I just don't have loops anymore. So it doesn't make much sense if I just try to build on what I observed in the first terms of array programming. So my question is, how is that possible? It should be faster. So about indexing, it has some potential, definitely, because in the case where the value of L is pretty small, it's actually a lot faster. So that's cool. But it gets terrible with matrices going being bigger. It actually gets terrible. So indexing is okay unless I replicate the data. If you remember this, I basically just replicate n times the columns and n times the lines. What I do here is that I build a huge arrays in memory and I play with them. The operations in themselves are not slow. What is slow is the copying of the data. That takes a long time, and you probably don't want to lose time on that because it's meaningless. Basically, copying multiple times the same things on the memory, you probably want to avoid it. Okay. So how do I deal with this situation? One way of, well, not removing it, but reducing the effect is broadcasting. It's another method that is the thing you should use in this situation. So I won't go through all of it, but the base concept is that binary operations, like the multiplication, for example, element-wise operations, will fail if the two arrays are of different shapes. Actually, we already met that when I needed to use the transpose of the equals matrix. Unless they can be broadcasted together. Here, I have some examples on when you can broadcast and when you cannot. I will move directly to the next slide. Again, all of that is on the Indico website, so you can download the notebook and the PDF to try the code yourself or have a look by yourself. So if I want to broadcast arrays, so I want basically to have all dimensions that are equal in number. So if I have an array with 3 dimensions, I want to have another array with 3 dimensions. Once you have that, you look inside of it, and every time you have a dimension that is not the same, one of the two must be a 1. If that happens, it means that, okay, you can broadcast it along the array. So you basically, as if you were copying it on that array, but you don't copy it, but you just read it several times. So NumPy knows how to do that. So it should be faster. It may seem a bit abstract now. Yeah, you can do it without the same shapes. Don't do that. Reshape everything all the time. Reshaping doesn't copy the memory. Basically, just interpret the array in a different time, so you don't lose time here. So you should always reshape your arrays. In practice, it takes that shape. So I have 2 matrices as usual, A and B. And I know that A is m times L, but here I have a 3rd dimension, which is L. And B, I had a 3rd dimension too, but before. So it's 1 L m. Okay. So now I move from a 2-dimensional space in a 3-dimensional space. Why do I do that? Because if I don't do that, I cannot multiply them together element-wise. Okay. When I do this, I have again take the shapes. I cannot say that enough. You end up with well, it's not C matrix in this situation, but with an object that is shape MLN. So that's a bit much. I don't want that much, but here I have basically all the element-wise multiplication that that have happened once in one operation. And then I want to reduce, I mean, that's the next step. So I do reduce along the second axis. The second axis is the L. Okay? So I sum on that axis, and I end up with N matrix. This is my C matrix. As before, two operations, element-wise multiplication and reduction. Okay? It's not the same lines of code, but they are pretty similar to the thing I did for the single elements. But this should be faster, a lot faster than next number. So if I look here, I have 9.6. I think it's one or two orders of magnitude faster than the previous one. 6. What? No. Oh no. Okay. Okay. No, I'm not looking inside of the right function. Okay, we are 1.6 here, so it's actually faster. It's actually faster because previously we were on 7.6, so we are 7 times faster for the low values of L, and for the higher values of L. Here it was 4.7, and here we are at values. We are 2.7, so we are twice faster. So it's better. It's better. It's better than the previous one, but it's not that faster compared to the loops. So that's a bit disturbing, but I mean, it's about the same. So it's cool. It's a worst case scenario, it's about the same in my situation. So what we saw numpy previously, my next question is, can I compile that? So can I make it faster by compiling it? So I just take that, I know that function now, just the 2 lines that I had before, but I just make it JIT compile. By the way, this is 2 lines of code, so I shouldn't have the same issues on the swap function. And here I do 2 things. I have one JIT version and one full JIT version. The reason is that is because if you remember, I said this, I have no insights of what happens inside of there in the profiler because it is compiled. So I have a non-compiled version, so I can have an idea of what is going on inside. And I just try it. Okay, so first for my, so we are for the high values of L, we are twice faster. That's cool. And for the low values of L, we are -7. No, 6.6 actually. 6.6 would be faster. Yeah, actually it's a lot faster. So okay, we gain time. That's cool. I want to look inside of it just to be sure. We see that the JIT version actually is nice. Now the second loop starts to remember the 5% rule here. It's about 5%. I might start to have a look on the second for loop. It starts to be interesting. But yeah, most of the time is of course taken by this. This was expected. And by the way, the total time here for the main function is 11 seconds. So it's a lot faster than the 6 minutes and something than we had before. So yeah, now it's gonna be a bit lower level. I'm going to talk to you about SIMD. So if you use Python, SIMD is probably not the kind of thing you hear every day. But this is an acronym for semi-structured multiple data. This is something that happens in the CPU, but most on the GPU is the place where it happens the most. The idea is that the machine is not a human. A human think about elements in an array. Even when we talk about arrays as a piece we are working on, we always make element-wise operations. So we always think about elements. For the machine, it doesn't work that way. Machine works on registers. A register you have on the CPU, on the GPU. A register can hold more than one data at the same time, one piece of data, one element of your array at the same time. So on the CPU, for example, you have size 8, 16, 32, 64 bits beyond if you are in a GPU. So the idea here is, can I put 2 32 bits, for example, operands on one register and apply an operation only once, and it does it on 2 of them. So I basically just, for the same amount of time, I just have a factor 2 of all the operations that are 4. That's all the mathematical operations that happen on the machine. That's the ID. Can I do that? The answer is yes. That's the whole point of SIMD. So you fit as many elements as possible in a register, and you apply the operation once, because that's how a machine works. It works in a register, not on elements. Yeah, I'm not going to talk about handling loops, but the idea is you duplicate the inside of a loop. So I did talk about the loop. The gain in speed depends, of course, on the size of the register and the size of the data. If I have a CPU with 64 bits and I use 64 data types, it's one element per register all the time. I can't gain anything using SIMD here. But if I work with float 32, for example, I may have some gain. If I work on a GPU, I have a lot more than just two operands on one register, so it should be a lot faster. So here, something you should note here, I don't change the code at all. The code doesn't change here. I'm not changing the code. What I change is this. So I just translate my matrices as type 64. They were already 64, but I make it explicit here, and as type 32. Floating point 32 bits is most of the time precise enough for pretty much any operation you do, unless you're doing physics at I don't know, pretty high level, and you need that level of precision. Most of the time, 32 bits is enough. And it may come with some nice figure, like the speed, for example. So same code, I didn't change anything, but just the data type changes. Okay, I do it for the two main functions, and I check this. Okay, so for the low values of L, okay, it's slightly faster, but not that much. We see that on the better math mode. That was the full numpy implementation. And but for the high values of L, actually the gain in speed is pretty impressive. For that, especially we move from 2 × 10⁻⁷ to well, half the amount. So that's nice. I didn't change the code. I just changed the data. Okay. I just changed the data. That's basically just a free speed up. Okay. So can I go further? No, I'm going to go even further. Talking about memory layouts. Matrix is 2-dimensional, as you know. But I cannot represent a 2-dimensional array in the memory. That doesn't exist in memory. Memory is 1 dimension. So at some point, I need to write the elements one after the other in the memory. There are different ways of doing it. Historically, two most famous styles is the C-style arrays, where they are row major. So I write one row of a matrix, then the second row of the matrix is written just after, and so on. Fortran had another approach. It was writing its matrices a column major. So one column, the second column, and so on. If I want to access one element and its neighbor, it's easy if they are stored in memory such that they are actually next to each other. If they are not, then I need to move further in the memory. This has an impact because when I want to fill the registers of my CPU, if I start in some address in memory and I just say, okay, load the next 64 bits, it's easy, it's one instruction. If I need to say, okay, load 32 bits, and then I need to load some other 32 bits at all, further, it's 2 instructions, take a longer time. Perhaps I don't want to do that. If I can avoid that, perhaps it's better. So in Python, this is a kind of consideration you shouldn't have, but if you know about this, you can gain some time. Okay. So nice thing about numpy is that you can specify it. Here's the different cases. So the contiguous case when you can load one block of the memory in a single instruction. Non-contiguous is when you have to find them wherever they are in the memory. So yeah, the code here is a little bit clipped, but I'm asking you to trust me when I tell you that the next part of the line is the same, except that the order is C. The order in numpy is for F for Fortran, so column major is for order F, and row major is order C, C and F for C and Fortran. I tried to two different orders, so F and C and F for both scenarios. Now, the reason why I'm interested in that basically is that because I never addressed the A matrix column-wise, only row-wise, and the B matrix because I never addressed it row-wise, only column-wise. So I would expect that one, the second one, to be faster because all elements on the same line on A would be contiguous in memory, and the same for B and the figures. Okay. So what can we see? For low values of L, the first one is actually a little bit slower in the OGIT version. It's weirdly enough slower, actually. I said so. It's actually faster in the OGIT version, but it's actually weirdly enough slower in the second version. Okay, so that's an issue. But then when I increase the values of L, I can see that there is some pretty huge speed up for the OGIT version. Here we move from 3.7 to 6.6, so that's quite a lot. And there is some non-negligible increase from the layer in the loop node to the next one. Okay, so this is useful, but when you have matrices that are big enough for you to see the increase in speed. Okay, so that's nice. So what did we learn about vectorization? Array programming is great. Yes, speed up I had was there, but use it with caution. The best approach may not be easy or intuitive. Thinking in n dimension, moving one dimension up is not always easy to think about. Compiled loops may be faster. The Nimba version actually is faster than the no loop at all version. So that's something you need to consider. And the Nimba version is easier to kill, basically, because it's just having loops and one single code to a function. Especially true if you use indexing and masking techniques. So noting the data type is important, and the order of multi-dimensional arrays may have an impact. So if you know in advance how it works, you can use that. If you have knowledge about your specific problem, you can use that knowledge in order to gain speed. That's nice. Yeah. Little word of warning: such optimization is very specific to using arrays, and it's often very low. I mean, here I'm talking about matrix multiplication. I would expect that your project, whatever you're doing, is a lot larger than that. So here I can spend a long time on that, but actually in everyday life, this doesn't make any sense. I wouldn't do that level of optimization on something as simple as that. So always use the profile at higher level to actually pinpoint the actual hotspot of your code. Okay, I keep that here. So now I'm moving to actual parallel execution. So here we're going to talk about multi-threading, multi-processing. It's an interesting subject. So the concepts are that I have parallel execution, so different processes or threads working at the same time to do different things or the same thing, but in parallel. So I should learn speed here. So a bit of theory. Your program can fork. So when it forks, it creates two processes. One is a parent, one is a child, and then they can work at the same time. Okay? From the OS point of view, each process is a different actual process. So they have their own private space in the memory, all the resources, all of that. It is forbidden for a process to have a look on what happens in another process. So because of that, you need to set up communication. You need to handle the communication between processes. It's not obvious that the processes can communicate, but you have a lot of different ways to do it. Pipes, shared files. I mean, the disk, of course, is common to everyone. MPI that you most probably already have heard of. Sockets if you use the network. Yeah, because processes can be on different machines, like client server, for example. They can communicate through sockets. Shared memory is one thing we're going to talk about here. Multi-threading is a different approach. Your program is one process, it can have different threads of execution. And because it's not a different process, it can access the same parts of the memory. But this can lead to some issues. Everything related to concurrent access. So if you have different threads of execution that try to access some resources, do the same thing at the same time, it can get very messy very fast. Imagine a room where everyone talks at the same time, you have no idea what to parse. If you just say, okay, you, then you, then you, then you have the information. So information comes faster when everyone is talking, but you cannot get any of it because it just messed up. When you actually synchronize everything, then it makes sense. Okay. I won't go too deep into that. Now, Python has a very strong opinion about multi-threading, should I say. Python does not want race conditions at all. Every problem related to multi-threading, Python doesn't want it. And it does it by having a global interpreter lock. A lock is a very simple object. You can do only two things with it. You can lock or release the lock. And the idea is that you use that object to protect actually some parts of the memory or the execution from one thread to another. So one thread is allowed to, in Python, one thread is allowed to execute something only if it has the GL. You have no control on that. Okay? So the locking the GL is automatic. Then your code runs, so one line of code runs, and then it releases the GL. And this happens at every line of code in Python, unless there might be some local optimization done by the interpreter, but it's the general idea. Okay? So you cannot have different threads working at the same time because the first thing they have to do is lock the GL, and if it's already locked, so if it doesn't been released by another thread, the thread just puts on hold. It waits until it is available. Okay? Because of that, even if you have a multi-threading library in Python that allows you to spawn different threads, you will never have more than one thread executing at a time. So you basically lose the interest of multi-threading in Python, but multi-processing is allowed in Python. What happens when you create a new process is that you create a new process. So the process is not your code, it's the Python interpreter interpreting your code. So you have two different interpreters that work concurrently with two separate GL. That's why you can have actual parallel work. But here the problem is not the same because you have to explicitly allocate shared memory, files, all of those communication mechanisms to have your processes communicate together. So you basically bypass the problems that is posed by a GL when you do that. And in Python, that's the only way to achieve true parallelization. If you use some libraries that actually do multi-threading inside, like in C and C++, they don't need to care about them because they do that inside at the lower level than Python. Okay? So here I am going to use this. This is very important if you want to do parallel execution, especially on the cluster. This is what I do on my computer when I know I'm never going to run that on the cluster because OS CPU count it's pretty safe. It's the number of cores I have on my computer. This is the number of cores that you can use. There is a distinction on the cluster because if you just use OS CPU count, you'll have the number of CPUs you have on the CPU. But maybe you ask for less cores than is actually available. So you want to use the first one. I know it's a bit lengthy and it's really not obvious, but this is what you should use. Otherwise, some admin would probably just shut down your process because you use more processes than you're allowed to. So don't do that. I mean, it will save us work and it will save you time of compilation because yeah, that's not how you should work. Yeah, so PSUtil I'm going to use only for that. The reason why you need that. And multiprocessing is the library I'm going to use. Not multi-threading, multiprocessing. And I'm going to do this. That's the same thing you saw already, except that here I unpack the arguments explicitly inside because I will receive a tuple arguments rather than arrow and vehicle hello. Okay. So here, what I do here is something that again you should do because it saves you a lot of work. It's instantiating a pool of processes. So what I say, when I ask multiprocessing to do that, is that I don't want to care about the number of processes, how they are working with it. I just want multiprocessing to provide me an object where I can just, okay, this is a work to do, deal with it, do that for me, okay? So this is the concept behind it. There is a bit more than that, but that's the general idea. I also define chunk size. So this is the number of, well, the amount of work each independent worker should do. and this is basically the number of cells for which I will have a parallel worker divided by the number of threads I will allow myself to use. And this is the list. Well, it's not a list; it's actually a generator. But this is the sequence of arguments that I will use. So if you remember, that is the thing that will happen here. Okay? So this is the code of my parallel workers. Very simple, but that is going to run in parallel. We will receive that, so it's a row and a column. Okay? So as you can see here, that here is a tuple. The reason why I do it that way, this is not a list. This is not all that. Oops. Yeah, that's a bit far. I discovered new shortcuts in my computer the worst time possible. Here. The whole thing here is not a tuple, and it's not a list, it's actually a generator. It's pretty nice because it doesn't do anything. I'm just instructing Python, okay, this is how you create those arguments, and it will be called only when the pool will need it. And the pool itself, I will use this. It's RMAP, there are different methods of the pool. And there again, this won't do anything. I need to ask the map to translate into something that actually is a collection of values, like a list, for example. Okay? Because a map object is just a map object. It instructs Python how to do things. It doesn't do anything. It just waits for us to ask for it. Okay? So I use C flat, so that's the flat version of C, because it's row major, and now it's going to work. It's I first, the row first, and then the column. So that's the parallel version of my code. Now, I also want, if you remember previously, 10% of the time I'll spend on the inner loop of the two loops. So the idea is, okay, can I have some sort of hybrid strategy where I have both array programming and parallel worker? Here, it's the idea. I'm not going to work on one single element at a time, but I'm not going to work on the full matrices at a time. I will work on the one row of matrix A and the full B matrix. So I will compute one row of the C matrix at a time. Okay, so it's kind of a hybrid situation. Of course, I expect to have less work to do because there are only n rows and not n times n cells. So we should have less workers, less work to do. Well, the number of tasks to perform is lower, but the work to do is actually higher in each of the different workers. So I'm interested in, okay, is that better? Is that better? So I have two contestants now to know which one is better, and I have a third one, which is numba. Numba is amazing. You can add this, so you can instruct numba to go parallel. Okay, this is very super nice because when you look at the code, it looks like normal code. It's just that's the difference. I mean, the parallel equals true, of course, but this is the difference. I don't use range. I use numba p range. And when I do that, I instruct numba that this loop actually should be parallel. So numba will instantiate some loop, some pool of threads here, actual threads, and parallelize that work here. And if you look at this, this is the hybrid version. So it's I make things row by row and not cell by cell. Okay. So those are the three approaches I have. And we can see that there is pretty clear winner here. I mean, we are at 0.1% of the time compared to the others. So that looks cool when we compare them with the other. Here it's also pretty fast, but I just I'm curious about the amount of time it takes. If I look at the best one, it's for the low values of L. Here I have a yeah, 0.5 times that's that. Okay. For high values of L, we are at 8, no, it's 4, 6, 4, 6, and here 2, 6. Yeah, okay, 4, 6, and 2, 6. Problem here is that we are not really faster actually. So we consume more resources, we make things in parallel, but the code is actually slower. So it's kind of a Microsoft situation where you use a lot of resources to do things least efficient way than if you use only one single thread. I mean, that's definitely not ideal. Okay, so all of that for nothing, that sounds a bit bad. Now, the thing is, we are going to investigate on that. So if you remember, processes have to communicate. I didn't do that. We don't care about it. This instantiated pool of processes and that's it. So the communication is, that's because the communication is simply handled by the multi-person library. It's implicitly handled by the multi-person library. So what happens is that basically Python has to make some sort of binary string of a string of bytes that represents the code to run and the data, the input of the code. And that takes some time because we need to translate whatever it is to some byte string, and then the process receive that byte string and translate that back into some code and executable code and data. Okay? This may take a long time. Actually. That's why the one where I have one thread per cell takes a very long time because that work is on all of the cells. So here I'm investigating the use of shared memory. So the idea here is to copy what I need inside part of the memory that is shared across all processes. So I don't need to make that message passing work all the time. So because it is global, not local anymore, the access to the data will be a bit slower. Okay, but I save time on the copying part. Okay, yeah, the time to start a thread will be process will be a lot shorter. And again, it depends really on your approach and the data you have. So profile and choose, and there is no good solution. There's several good solutions. You need to choose the best one. Now, about the concurrent access. There are a lot of weird scenarios. I will just cover the three main review. If you have different processes that try to access memory at the same time, you have a scenario where if two processes try to write at the same time, this is the worst because they can corrupt data, they can erase previous values. It's you definitely don't want that scenario to happen. If you have one that writes and another that reads, the one writing would probably finish, no problem. But the one reading may read some data because it could have the beginning of some data and the end of some other data or some mashup in between. I mean, that's definitely not ideal either. And the third scenario is actually pretty much okay because if several different processes read at the same time, they don't modify the data. So they can do that. They can do that without any precaution, but that works. If you are not sure or if you are afraid to investigate further, you can just use shared memory protected by default by a lock that is provided to you by a multi-person and ignore all of that. But if you know what you're doing, and I assume I know what I'm doing, if you know what you're doing, you can disable that. So you lose the time overhead of locking the shared memory. So you can access directly because you know that you won't break anything. Okay, so in this situation, A and B, matrices A and B, are never written to just breadcrumbs. So this is scenario 3, it's a safe one. I can disable the lock on P. C is only written to, so that looks a lot like the scenario 1, but the different child processes never write on the same parts of matrix C. So am I really on the scenario 1, or can I do some safe things here? Spoiler alert, actually I can do that. And I will use the big stuff here. We are not talking about the same kind of matrices anymore. It's a lot bigger, and in this situation, it makes sense to actually use multiprocessing. It doesn't make sense to use other approaches here because data, well, it makes sense, but it would take a lot longer. So here it makes sense actually to do that because the data is sufficiently large. Okay. As you can see, I have only 3 of them because otherwise it was taking too long. So don't do that. Try to have more than 3 pools. And I am doing this. I initiate the pool with this. So it's actually very simple. I just declare 3 global variables, A, B, and C. And I store their respective arrays into those 3 global variables. And here, this is this is the same ln in place function I have, you would realize here that it's not compiled because it wouldn't work otherwise. It wouldn't work because I don't need A and B passed through the args actually. They are already available. I don't have A and B here. Okay? I can use them as if they were magically present. And I do it here by the differences here. So the number of threads does not change. The initializer is actually the function I just defined previously, and the init args are the three matrices. So matrix C, I started like this. I'm going a bit faster because we are short on time. If you have questions after the talk, don't hesitate. Here I instantiate some array using multiprocessing. Don't be confused by NP and MP. They are two different things. So here it's multiprocessing. I'm asking it to instantiate an array. So that's memory. So it's one dimension. So I need n times n cells of float 32. It's a different type, but it's actually, you can recover it through numpy that way. Okay. Once I have that, I have a very convenient array because it's one dimension. We would prefer to have an numpy array, which is nice because numpy allows to build an array from a block of memory here. So I make it from buffer, and then I give it the array I just created. Okay? I specify the type, the data type, of course, otherwise numpy cannot know what it is. And I reshape it in n. Okay? So that's nice. I need to do some work, of course, for A, B, and C, and I do it. Yeah, I do the same approach than earlier. I want to try the hybrid version where I have one part array programming and one part multi-processing. So here it looks a bit weird, but this is basically reshaping the array. Just like dot reshape, what's another syntax. And here I take one row of A and the full matrix B. So that's the same idea, just slightly different syntax. So I have fewer workers, but I have more work to do in each separate worker. Okay? And I tried those four ones, those two that actually were not shared memory. So also the OG, so the full number version. And those, so the row part, so the one I just showed you, and the one where I just compute element by element using shared memory. And I use some work here. So I create arrays here, and then I copy the matrices I have inside of those arrays, so they are existing inside of a shared memory. And then I just reshape them as I want, and I can move them. And this is the results I have. Okay, so I cannot compare with the full numpy version. The reason is that if I try to do that, I don't have enough memory on my computer to do so. So we are in a situation where the most efficient code we have so far actually does not work because of technical constraints. Like the amount of RAM I have on my computer is not enough. This is a situation where sometimes perhaps the best algorithm that exists is not the best one because it does not work. It simply does not work. So here I have to work row by row, element by element, but I cannot move one dimension up, then to reduce to 2 dimensions. That doesn't work. And well, this one is the worst, but that was expected. This one is the second worst, but this is not shared memory. This one actually, and I'm pretty proud of myself here actually, because I managed to do something better than Numba without using Numba. But you saw the amount of work that requires actually. It's a lot of code and it's a lot of understanding what is going on. If you don't want to struggle just with the Numba version, it would be slightly slower than in the best possible implementation. But that's the idea. So wrapping up very fastly. So there are two main ways of doing more work per unit of time. So vectorize your data. I mean, there are at least 2 times where I just gain speed by pre-processing my data. I didn't do anything about the work, about the code, just pre-processing my data. So that's one way to do it. Array programming is really the thing you should do at when you can do it, but make it in a sensible way. And don't do stupid things. Try to use it nicely. And execute operation in parallel if you need it. If your data is sufficiently, it makes sense. Otherwise, don't do that. So you augment the number of parallel workers. The overhead may be heavy. So if your data is large, use shared memory. Otherwise, you have a lot of message passing, but actually just an overhead, just nothing except copying data. It's better used at higher level, so don't try to deal with the threads directly, otherwise, unless you actually know what you're doing, because it can get very messy. And yeah, it's more powerful if the workload is heavy and the row by row. It's more powerful than the element by element because the amount of work is higher, but well, it is not that slow. And what is the best strategy? There is no best strategy. It really depends on your use case. That's why there are so many different approaches, because every time one is better than the other for some reason. Okay, the reasons depend on your context and your use case. Yeah, if you have a dubs, there's different approaches, and just choose the best, because there is no magic way of doing things fast. You just try and see. And that is important. I show you something where I go really deep into detail, so you know about these things. I'm not telling you that you should do it. If you do need it, by all means do it. But really, if you can just settle on a suboptimal solution, for example, the numpy solution was pretty easy to set up, but that is easy and fast to develop. Then you can come back later and optimize further if you need to. This is it is a bit counterintuitive, but when you optimize large projects and you focus, some points actually take a long time, and you just settle on a suboptimal solution. For all of those points, you gain a lot more time than when you focus on the most time-consuming point of your project, and you optimize it to the point where it's just insane the amount of details you go through, because it requires lots of time to optimize. You would gain a lot more time if you actually optimize the project as a focus on the most important thing, and you check what is the most important time consumer after each iteration of optimization. Okay, so that's all for me. Yeah, I'm 10 minutes late, so that's kind of okay. If you have questions, again, everything is on the website, because you can download it. It's actually it's actual code, so you can run it yourself. This was the profile. This is a Jupyter notebook, so if you are familiar with that, you can just run it yourself. I just tweaked it a little bit so it looks nice in the presentation, but you can download it and use it yourself. It's meant for that. So that's it for now. Yep.
Do you think the work that is going on about moving the global lock in pattern will have an impact on what you just explained?
If it's the case, I'm worried for next year. No, but I think it's a good thing, because it doesn't make much sense to have a multi-threading library and not have parallel execution with that's. There are some cases where it actually makes sense, but they are so niche. But no, I think it's a pretty nice thing, because then we would have a. I don't know what's going to happen basically, but if you have a per objects lock, a bit like in Java, if I'm not mistaken, perhaps we would have an increase in speed and easier multi-threading. I mean, as if I am instantiating shared memory in multi-processing, is the idea. I have one node by a block of shared memory by default. So if I don't do anything, it works like that, and I cannot have different processes or threads operating on the same part of the memory. I think that way is probably better for multi-threading, but again, that's the choice of implementation of Python. Then most of them have their reason, so I don't know. I hope so for Python. I hope not for that presentation, but that's me being lazy. So, other question?